Ever wonder how something like ChatGPT or Google Translate actually learns to read our language? I mean, it feels like pure magic, right? But it all starts with one single fundamental step. Today, we're going to unpack the roadmap to understanding that step, kicking things off with the biggest question of all. Right, this is the core of it. For a computer, a sentence isn't about words and meaning. Nope, it's just a long, messy string of characters. So before any kind of real understanding can happen, we've got to break that string down into pieces the machine can actually work with. And that whole process, that's called tokenization. So to get our heads around this, we're going to follow a really clear 5-part roadmap. We'll start with the why, the big picture. Then we'll get into your high-level strategy. After that, we'll tackle the messy reality of real-world text, peek under the hood at the pipeline, and finally, it will meet the algorithms that do all the heavy lifting. First things first, why even bother with this? Well, it's because a machine learning model doesn't see words or sentences like we do. It only sees one thing: numbers. Tokenization is the essential bridge between our world of language and the model's world of math. It's the universal translator that makes everything else possible. Here's a great way to think about it. If your text data is a big pile of ingredients for a recipe, then tokenization is the kitchen prep. It's the chopping, the dicing, getting everything into manageable pieces, those are your tokens, before you can even think about starting to cook. And these tokens, they can be whole words, single characters, or something in between called subwords. Okay, so before you start chopping, you need a strategy, right? You don't just grab the first knife you see. In natural language processing, you have to make some really important decisions right at the start that are going to affect your entire project. And here's the first big one. Do you even need to build a tokenizer from scratch? Look, most of the time, for common languages like English, the answer is no. You can just use a powerful, pre-trained tokenizer that comes with a model like BERT or GPT. You'd really only train a new one if you're working with something super unique, like specialized medical jargon or maybe a language that doesn't have many resources yet. Next up, if you are training one, you hit this critical choice. How are you going to load your data? You could try to load all your text into memory at once. And sure, that's fast, but if you're working with gigabytes and gigabytes of text, your computer is just gonna give up. It'll crash. The much smarter, safer way is using a generator. It just feeds the data to your tokenizer in small, bite-sized batches. It's absolutely essential for any serious large-scale project. And speaking of large scale, you'll hear people talk about fast tokenizers. Why is that a big deal? Well, these things aren't written in Python. They're built in super fast, low-level languages like Rust. What this means is they can chew through huge amounts of text at lightning speed. And that's not just a nice to have, it's a must-have when you're training a massive model or trying to serve millions of users in a real-world app. Okay, our strategy is set. Now, let's get real. Human language is messy, right? It's full of names, super long sentences, typos, weird formatting, all kinds of chaos. So how do these modern tokenizers actually handle all of that? So let's take a name, like Marie Curie. A tokenizer might split this into 2 tokens, Marie and Curie. Or maybe even 3, like Mar, E, and Curie. Now, here's the cool part. The model is actually smart enough to learn the relationship between these tokens. It figures out, hey, these pieces usually show up together, and it learns to recognize them as a single idea. It all comes down to learning context. And what about those crazy long paragraphs you get from a legal document or a novel? Language models, they have a fixed input size, like they can only read 512 tokens at a time. So what happens? The tokenizer has a plan. It can either just truncate the text, basically just chop it off at the limit, or you can set it up to split the long text into several overlapping chunks. That way, it makes sure the model eventually gets to see everything. This brings us right to the pipeline itself. We've talked about what it does, but now, let's pop the hood. Let's take a look at the step-by-step process that's actually happening inside. It's a really clear sequence that makes total sense once you see it all laid out. So before the main fancy tokenization algorithm even gets to see the text, 2 super important things have to happen first. They are normalization and pre-tokenization. Think of these as the essential prep work before the main event kicks off. So what on earth is normalization? Well, if we go back to our kitchen analogy, normalization is like washing and peeling the vegetables. It's all about standardizing the text to get rid of the noise. This could mean making everything lowercase, stripping out accents, or dealing with weird Unicode characters. That way, the model sees café and café as the exact same thing. All right, after everything is cleaned up, we get to pre-tokenization. This is the rough chop. The pipeline does an initial split of the text into bigger chunks, and it usually does this based on spaces and punctuation. This gives you a list of words that are then ready to be fed into the main, much more sophisticated algorithm for that final precise cut. And that brings us to the main event, the algorithms themselves. These are the really clever methods that take those pre-tokenized words and break them down into the final subword tokens. And there are a few major players in this game. First up, you've got byte pair encoding, or BPE. This is a classic bottom-up approach. It starts by treating every single character in your text as its own token. Then it looks for the pair of tokens that appears most often, say E and R, and it merges them into a new token, It just keeps doing this over and over, building up a whole vocabulary of common subwords right from scratch. Next, there's word piece, which you might know from models like BERT. It's kind of the opposite of BPE. It starts with a big vocabulary of all the basic characters and then works to combine them. But instead of just grabbing the most frequent pair, it picks the merge that makes the training data most likely, statistically speaking. It's a slightly more clever way of figuring out the best way to combine pieces. And finally, there's the unigram model. Now, this one's really different. It starts with a massive potential vocabulary and then intelligently prunes it down, getting rid of the tokens that are less useful. But the most fascinating part is that it's probabilistic. It can actually come up with multiple, different, valid ways to tokenize the exact same word. This can make a model more robust, because it learns not to get tripped up by just one way of seeing things. So let's pull all these pieces of our roadmap together. The real key takeaway here is that tokenization isn't just mindlessly splitting text. It's a whole strategic pipeline. It starts with big decisions you have to make about memory and speed. Then it moves into cleaning and prepping the text. And it all ends with picking a powerful algorithm like BPE, wordpiece, or unigram to do that final precision work. Honestly, understanding this pipeline is the key to unlocking how modern NLP really works. It is the foundation that everything else is built on. So now that you have the map, there's really only one question left. What are you going to build with it?